Tracking of catheters under fluoroscopy has been achieved by placing radiopaque marker bands at the catheter's tip, as shown here. This provides an estimate of position of the catheter tip, however neglects to track the orientation in a planar image, as evidenced by the simulation, where the only indication of rotation comes from the moving coordinate frames. When navigating steerable or robotic catheters, it is critical to track this orientation to safely manipulate the catheter. This is especially relevant for the extremely long, slender catheters in the brain, which can experience significant torsional losses along their length. Existing works aiming to track catheters fall into sensor-based and image-based approaches. Electromagnetic tracking requires coils placed in the catheter, which provides complete pose information but lacks shape information and is hard to miniaturize for thin-walled catheters. Optical fiber approaches such as fiber Bragg grating sensors can provide shape information but are expensive and sensitive to thermal effects. Many works have reported segmentations of catheters as a spline, assuming the material is radiopaque, but does not capture rotation along the backbone. As previously mentioned, segmentation of marker bands captures position information at discrete locations, but does not inform shape or orientation. Our approach builds off of existing works by using existing clinical imaging to capture complete shape and pose information without relying on additional sensing modalities. We achieve this image tracking by placing radiopaque marker bands at specific locations along the surface of the catheter. This enables us to discern rotation along the backbone, as shown in simulation and from fluoroscopy on the right. Our estimation approach first relies on segmentation of these markers in two imaging planes, then reconstruction and finally solving the shape and pose from these estimated marker locations. Segmentation consists of thresholding for the radiopaque markers, detecting maximally stable extremal regions, and isolating the centroids of each marker. Once segmented in both image planes, the marker locations can be reconstructed in 3D space by using the projective geometric properties of either imaging plane. Once the locations of each marker are estimated in 3D space, the modal coefficients describing the catheter shape, C, and the rotation about the backbone, sigma, are estimated using a sequential optimization framework. Upon convergence, an optimal shape and backbone rotation is found, which is the best estimate of the current catheter configuration. To evaluate the effect of the radiopaque marker placement, we simulated the catheter throughout its workspace with randomized marker position uncertainty to simulate the effect of segmentation noise. We found optimal estimation results when the markers are spaced between 2 and 3 times larger than the uncertainty due to image segmentation. If they are spaced too close together, the reconstruction can invalidate the segmentation. But if they are spaced too far apart, the estimation signal attenuates. We evaluated the effect of the catheter design itself, specifically looking at the catheter segment slenderness, defined as its length over radius. For highly slender designs, the estimate of backbone rotation begins to suffer for slenderness greater than 60, while for slenderness less than 25, both shape and roll error suffers. Points may be lost in segmentation due to occlusion with anatomical artifacts or point correspondence on epipolar lines. We simulated the algorithm's performance when up to half of the catheter's markers were dropped, and showed that despite some expected loss of performance, RMS errors were still found to be within a clinically useful range. A 2 mm diameter prototype was made using a tecothane catheter with tantalum markers placed along its length at measured locations. This prototype was imaged under biplane fluoroscopy in different bending configurations, with fluoroscopic images collected for each. Across 29 different configurations, the shape and backbone rotation were computed following the estimation approach. The RMS error across all estimations was reported as 1.14% of the catheter's length, indicating high shape tracking accuracy. The error of the backbone rotation was found to be on average 28 degrees, which is acceptable considering torsional transmission losses can be as high as 180 degrees. An additional 1.4 mm outer diameter prototype was made from a standard microcatheter and was inserted in a mock vertebral artery. This demonstrates intended clinical use of tracking catheters within the neurovasculature.